So here's a quick explanation on RCL circuits. Here we have a GW Instec oscilloscope. It's a digital storage scope, and on the right we have a GW Instec signal generator, audio generator, and then we have the Pasco RCL board, which is standard Pasco product, and the part number is a CI6512. Now, the problem that most physics teachers encounter is the fact that they use the standard leads that are supplied with an oscilloscope, and the one side is connected to earth. If you now look at the board, you'll notice at the top of the board on the left hand side we have a circuit. Towards the left we have a signal generator. The one side of the signal generator is grounded. This is called an unbalanced feed. Then we have a resistor, an inductor, and a capacitor. You can see the values there, 8.2 millihenries and 100 microfarad respectively. Now, what happens is, looking down below, you'll see there's an oscilloscope. There's the two channels, and they are also, one side is grounded, also an unbalanced feed. If you look at the left hand side, you'll see the mains connection. It's also earthed. This is obviously a safety factor, and if that earth is removed, it will then pose a danger to both the user and students, which is obviously not allowed. So if you look at the circuit, and you can work it out for yourself, looking at the purple one, you'll see that 1 and 2 are connected across the capacitor, and you will notice that 1 is the hot wire and the 2 is the earth, and you will notice that also on the right hand side of the capacitor it's also connected to earth. So we end up shorting out that capacitor. So you can try multiple combinations of connections, you will always short out a component. So we have to mitigate this, and we have come up with a solution, and here is the solution. You will now notice in the middle of the board I've drawn the B and C connector, which is the common connector that's on the front of the oscilloscope. That's on the left hand side of the red diagram, and you'll see there's the symbol of a transformer, and on the right hand side are the two flying leads. So what this does is it isolates the earth, allows the signal to pass through the transformer. We know a transformer will pass an AC signal, so it allows the audio signal to pass through the transformer, but it lifts the earth from the signal, which now mitigates all those issues. And this is what the transformer looks like. You can see that. No, you can't see it. Whoops. So as you can see now, we have the oscilloscope's standard leads being used, and we have a signal on the which would be the second channel, which is across the capacitor, but in this particular case the coil is now shorted, and that's obviously not going to work for us, so we cannot see any signal from the coil. So we have to remove those and put in the electrotest ETL ISO transformers in place of those leads, and let's see what happens. So now I've replaced the oscilloscope's leads with the isolating transformers, and you can see that we have a voltage display across the inductance and the capacitance. Now what we're going to do is we're going to vary the frequency on the signal generator, and we will then monitor the display of on the oscilloscope. So we go down in frequency. As we go down in frequency, we can see the voltage across the we've gone up in frequency. The voltage across the inductance has increased, which is what we expect, and the voltage across the capacitance has reduced, and we go down in frequency, and the converse happens. Just need to change the time base here. We can see now the voltage across the inductance has reduced and the voltage across the capacitance has increased. Just go find the stage where both are equal to each other, and that's pretty much, I would say, there. And if we look at the frequency, it says it's 16 times 10, which is 160. And the feature about this oscilloscope, which is great, if you push the measure button, you can see down here some parameters, and there we can see it says the frequency is 160 Hertz. Now we will apply that in our formula, and we will see what we get as the calculated resonant frequency.